Hello everyone. In this presentation, I'll be going through a few security technologies that can be used in storing the data securely, that can be used in authentication protocols, etc. And I'll be going through a few multi-server authentication research papers and we'll survey through them. Here's the table of contents for this presentation. Firstly, I'll be going through research papers on multi-server authentication protocols. Then I'll go through the technologies for secure storage. And then we'll go through a technology known as SIM overlays. And at the end of this video, we'll go through FIPS 140-2 standard. I'll also provide the links and references for this presentation and also the PPT file. Without wasting any time, let's begin with the presentation. This part of the paper will In this part of the video, we'll be going through a few research papers on multi-server authentication. The first one, a secure three-factor user authentication protocol with forward secrecy for wireless medical sensor network system. What this name says is that this is a three-factor user authentication protocol for medical sensor network system. What a sensor network system is basically a collection or a number of sensors or IoT devices that are connected for a particular application. These IoT or sensor devices, they are connected to a gateway. This gateway basically helps collect the data in all one place. The user, he connects to this gateway, and using this he can control those sensors or IoT devices, and he can also collect the data. Now the building blocks of this protocol, elliptic curve cryptography. This is a public key cryptography technique offering a strong security with smaller key sizes. This is also a very efficient protocol. The diagram on the right, this basically shows an elliptic curve. The equation here, this is the equation for the elliptic curve, y is equal to x cubed plus ax plus b. Suppose this point P is a private key. Now we draw a random line from this point P, and the maximum number of points that this line can pass through is 3 for this elliptic curve. Basically these points, these are taken for public key derivation, and from this point P, which we consider the for the private key, which is also random, we basically for this point Q, we perform some mathematical operations like point doubling, point addition, or scalar multiplication. And once we perform an operation like scalar multiplication, we again apply the same operation, scalar multiplication, for the result with point R. Now basically the result at this point R will act as our public key. Now if we want a more robust and strong public key, we can again choose a random point. Like if we can draw a random line, say we take this point, and we can again perform this operation to derive another public key. Now the second building block, a biometric verification with error correcting codes and fuzzy commitment scheme. Biometric verification, biometrics is basically your fingerprints, your iris, or your facial recognitions. Now, error correcting codes are basically used to transmit data in a noisy channel. Basically, when errors are introduced inside the data, this error correcting codes helps to correct those errors. Here, fuzzy commitment schemes, they help us use these error correcting codes inside our biometric verification. Whenever a slight variation is there in the biometric data, the biometric data is still considered valid. The fuzzy commitment scheme that is used in this protocol is Bose-Chaudhry-Hockenheim code, BCH codes. Now the next building block of this protocol is honeypots. Honeypots are basically traps for cybersecurity attacks. In this protocol, how this is used is whenever a wrong credential is being entered, they basically store those wrong credentials inside honey lists, and they won't allow for the login process for that particular credential. We'll go towards the protocol. Here are the notations for the protocol. You can go through this. I won't be going through the details of this. I'll directly move towards the protocol. Here are the protocol phases. First, in the initialization phase, the registration server, it initializes parameters like elliptic curve, a hash function, etc. In the registration phase, the user selects a user ID and a password, and biometric information. The gateway generates the secret key for the users and stores them securely. The user sends the following data and the gateway generates the secret key, and it stores the secret key securely, and also it stores the honey list equal to null, meaning that the honey list, the user's credentials won't be stored, and this user is considered as valid, and it calculates some other hash values and it is sent back to the user, and the user stores it on his mobile device. Login and authentication phase. All this information here, it looks overwhelming. I'll just simplify it down and I'll summarize this for you. The user inputs his ID and password, and he also inputs his biometric data, and the verification of the user inputs are basically done on his own device. If the user is identified as authentic, then the mobile device and the gateway perform mutual authentication, and the mobile device and gateway, they perform mutual authentication using elliptic curve cryptography. Similarly, after this process is done, the gateway also calculates its own values and then sends it to the sensor, and the sensor and the gateway also perform the mutual authentication using elliptic curve cryptography again. Some other values and some other messages are also calculated during this process, which I won't be going through the details of. Let's go to the second protocol, a novel multi-server authentication scheme using proxy signature with scalability and strong user anonymity. The building blocks of this protocol: proxy signatures. Proxy signatures are basically a cryptographic technique that allows a user or an entity to convert its signature into another entity signature. For example, a user A can sign on a particular message, and then that message is sent to the user B. The user B uses this proxy signature and turns that signature of user A into his own signature, and this can be verified by some other entity. Bilinear pairing. Bilinear pairing, here this concept basically means that here something called groups are used. A group is two numbers which satisfy certain axioms, group axioms. These axioms are the properties like closure property, associativity, identity property, and inverse element property. If two numbers satisfies these particular axioms, then they are considered to be a group. In bilinear pairing, two groups of elements are combined to form a third group of elements. Now, this bilinear pairing property is also seen in elliptic curve cryptography. If you consider 2 points on the elliptic curve as a group, like the in previous elliptic curve we saw 2 points. Those points, if you consider as a group, after performing a particular operation on the top on those 2 points, it gives us a third point as the output, a third group as the output. Moving on to the protocol, the notations table is not present in the research paper itself, but you can go through this notations table which I created. Now let's go to the user registration phase. In the user registration phase, the user enters his user ID and password, and the chosen mother server, he sends it to that. The mother server now generates a secret key for the user and a public key for signing purposes, and it also generates a signature key, resignature key for proxy resignatures. All these parameters and some additional parameters are stored on the smart card, and smart card is sent back to the user. Now the user, during the login and authentication phase, he enters his ID and password. He uses a fuzzy verifier to verify his password and tolerate minute variations. The smart card generates a login request and it sends it to the foreign server. When the user wants to authenticate to the foreign server, now the foreign server, what it does, it forwards the request to the mother server. The mother server verifies the user. The mother server then sends the confirmation message. Upon successful confirmation, it sends this confirmation message back to the foreign server. The foreign server calculates its own parameter and upon successful verification of the mother server and the user, it sends a message to the user, and the user then calculates a session key, and the session key is used for the rest of the communication. The proxy resignature, basically here it is used in a way like if the user signs a message to authenticate, the foreign server receives this signature, and this foreign server, after verifying the user, it uses its own resignature key and signs on that message. Now uh, this converts that user's signature into the foreign server signature, and upon sending that signature to the mother server verifies that signature of the foreign server and the user. Moving on to the next protocol, a secure three-factor authentication protocol for e-governance system based on multi-server environments. This is the notations table for this protocol. We'll move on to the phases of the protocol. In the registration phase, in the user registration phase, the user enters the user ID and password and his biometric data. The registration service issues a public and private key to the user based on this input. And e-governance registration, e-governance servers, they register to the registration server by selecting an server ID, and the registration server issues a public and private key to these e-governance systems, and it also stores the e-governance system shows their private key. Now, login and authentication phase. The user inputs his user ID and password and the biometric data on the mobile device. Now, the verification happens on the mobile device itself, and if the data is verified properly and if the user is valid, the session key is established and agreed upon between the server and the user. Several other computations happen while this login and authentication phase, which I won't be going through the details of, and I have just summarized the protocol for you. This SK is basically the session key. Now moving on, uh, an improved authentication protocol dependent on registration center for multi-server environment. This is the notations table for this protocol. Moving on to the protocol itself. Now the research paper didn't have any diagram, so I decided to keep the summary of it in this presentation. Now during the registration phase, the user enters his own user ID and password and a random number. He computes a hash of that user password and user ID along with that random number appended together, and then this ID and hash is sent to the registration server. The registration server computes its own parameters and stores these parameters onto the user smart card for further authentication. In the login and authentication phase, the user enters his smart card and inputs his user ID and password and computes the hash value back again. The smart card verifies the user's legitimacy by comparing it with the previously stored hash value. The smart card generates a random number and calculates a few other hash values and sends the login request to the server J. Now in the authentication phase, the server J chooses a random number and calculates its own values and sends the login request message to the registration server. Registration server calculates again its own parameters and verifies the authenticity of the server that sent the request. And upon successful verification of these parameters, the registration server computes the additional parameters and sends a mutual authentication message to the server J. And the server verifies this message and all the parameters of the registration server. And if successful, server J sends a message to the user I confirming the login. The user I verifies the authenticity of the registration server and the server with which it wants to communicate. And if successful, it generates a session key, and both agree upon a session key, and further communication happens. The password change phase is quite similar, so I won't be going in the details of that. Moving on to the next protocol, anonymity preserving round effective three-party authentication key exchange protocol based on chaotic maps. Chaotic maps. Chaotic maps basically they exhibit a chaotic behavior. These are the mathematical operations that execute a chaotic behavior, meaning that you cannot uh, determine how a particular value is being calculated. These chaotic maps that are used in this particular protocol are chaotic maps based on discrete logarithmic problem and chaotic maps based on Diffie-Hellman problem. This discrete logarithmic problem, this basically means that if there's a value x and a value y, and the value x went from x to y after some particular number of operations, you cannot determine the number of iterations that happened from going from x to y. And this property, we can see this property in elliptic curve cryptography too. If there's a private key and if a public key is given to you, you won't know how many number of iterations have happened in generating that public key. Now, chaotic map depending on based on Diffie-Hellman problem. What this basically means is that there are three values x and two of these are functions tr of x and ts of x, and you upon on generating trs of x, which is uh, which is applying this tr of x and ts of x subsequently, you won't know the number of iterations involved in this. How this matches with Diffie-Hellman is that if you go to the protocol, you can basically understand that the user selects some of the parameters and it uses its own function, say tr, and it calculates a particular value and sends it to the user b. The user b, if it selects a particular function ts, it applies that function ts on that tr, and similar calculation happens on the other user's end, and a particular session key is established. Going to the protocol itself, this is the notation table for that for this particular protocol. Now the protocol phases: system initialization phase, which is not in this slide, but I'll just dictate it to you. The server picks a large number of a large prime number and a seed value and a chaotic map. Now the chaotic map used in this particular scheme is Chebyshев uh, chaotic map or Chebyshев polynomials. It and then it chooses a secure hash function, etc. And after the initializations are done, the user registration phase. The user A this sends an identifier to the server through a secure channel. The server verifies if the user is already registered. If not, and if the user ID is available, it computes a value XA based on the user's input and this value S, which is the server's secret key. Now all the other values are calculated like a hash function, ek and dk, which are basically key values, and all these are stored on the smart card, and the smart card is sent back to the user. The user calculates its own values using the password and biometric data, and it stores them on the smart card of the user. This protocol basically is for a three-party authentication, meaning that three parties are involved. It can be these three entities can be two users and a server, etc. And in the explanation of this protocol, we are seeing that there's a user A, a user B, and a server S. Now going to the authentication and login phase itself, a user A initializes initializes the process by entering his user ID, password, and biometrics data and verifying using his smart card that was previously generated. The and these and a few other values are calculated, and he said this, the user A sends these values to the user B. The user B also authenticates himself by entering the password and biometric data by using a smart card, and the user B also calculates some other cryptographic values. And upon successful, the user B also verifies the user A, and upon successful authentication, the user B, he sends the request to the server yes. The server yes, it checks the authenticity of both the users, and it calculates several other parameters for all this communication. The user B and the server, they all have some temporary keys and temporary values stored. Now on the beginning they calculate their own key and some other temporary values like ZAS, this is a temporary value, ZBS, this is a temporary value, and etc. The server also computes similar kind of calculations, which I won't be going in the details of. After the successful authentication by the server, the message is sent back to the user A. The user A checks the authenticity of the integrity of the message, and also the signature of the server. And upon successful verification, a session key is established. This session key is used for further communication, and the user A, he sends a message to the user B, and the user B also computes the similar parameters and also a session key for further communication between A and B. Moving on to the next protocol, an enhanced and secure multi-server based user authentication protocol. This is the notations table of this protocol. Let's go to the phases of the protocol. First is the registration phase. The user initializes by using a user ID and a strong password and a random integer, and a pre-shared key is calculated between the user and the registration server. The user the user sends a registration request message with all these parameters, user ID, RP, which was calculated here, which is a hash value, and the registration server confirms and sends the confirmation back to the user, and the hash value is returned to the smart card. The user authentication phase. The user attaches his smart card, enters his user ID and password. The user ID is encrypted, and the password is also calculated. The password and the user ID and the random number, they are used to calculate a hash value, and some other calculations happen and a message is generated. This message is sent to the server. The server checks the authenticity of the user, and upon successful computation of its own values, it confirms the user, and it also checks the validity of the timestamp that the user is sending this message at. The timestamp is basically this TI value, and server sends back his own message M2 with its own timestamp. The user also authenticates the server and calculates some other cryptographic value, and user checks the validity of the timestamp. And upon successful verification, if accepted, the user sends a message back to the server confirming the authenticity, and upon successful verification, a session key is established between the user and the server. Moving on to this next research paper, a multi-factor authentication scheme for multi-server based virus application, and this is a review paper. This basically has a lot of like many protocols. There were some 8 protocols, and out of this first protocol we have went through this in this particular presentation, and you can see that what these uh, protocols are based on: the three-factor authentication, elliptic curve cryptography, etc., and they have used ban logic for verification of the protocol, for checking the security of the protocol, and they have used ProVerif. These protocols, ProVerif is basically an automated tool for checking the security of the protocol. Ban logic is a set of rules that are used to check the security of the protocol, and you can see what limitations are there in the protocols, etc. I won't be going through the details of this in this presentation. Now, in the first presentation, that in the first protocol that we went through, it says that user impersonation attack is possible. Here also you can see two-factor authentication based elliptic curve cryptography, and you can see that a lot of these protocols are using elliptic curve cryptography and fuzzy verifiers. So we won't be going through the details of this. And in the next paper, a survey on authentication schemes in multi-server environment. In this paper, you can see they have also done a survey on several protocols, and this particular protocol, we went through this protocol, and the security analysis is done through ProVerif or ban logic. Most of the protocols are using this security analysis schemes, and the cryptographic used techniques used in these protocols: symmetric encryption, decryption, a fuzzy extractor, etc. And the security features are also being mentioned in this paper. Similarly, the other protocols mentioned in that paper. Now, here we can notice one thing, that most of the protocols that are newly being introduced, they are using elliptical cryptography, because this is the previous time when I had gone through the research paper on elliptical cryptography, it showed that it was one of the most efficient protocols, and it can be used even in the resource constrained devices. And even being so efficient, it also provides one of the strongest authenticity to the users. It is basically strong as other algorithms, or even more stronger, yet it is also efficient at the same time. In this presentation, we'll be going through secure storage. Now, why is the secure storage important? Basically, if you consider any authentication protocol or any of the softwares that use your personal data or maybe your passwords, they all need to store some private information somewhere. For example, if you are using a password for a particular website, it needs to store the password hash or your private keys or any form of data somewhere in a secure form, so that they don't get in the wrong hands. So it's always important for any protocol or any system to have a secure storage for its working, for its proper functioning, and to provide you proper security to you. Now, firstly, we'll go through trusted execution environment. Trusted execution environment. What is this trusted execution environment? It is a hardware-based isolation on your chipset. Now, this hardware-based isolation, what it does is it creates a separate enclave where you can store your confidential data and passwords, pins, biometric data, etc. This provides features like confidentiality and integrity. This can also run tiny codes, and this also has its own clock and its own hardware like an full chip. Now, this also ensures the code is not tampered with while booting the bootstrap program. Now, it checks the integrity of the code before running the bootstrap program. Now, which devices support this trusted execution environments? If you have a mobile device, if you have a mobile phone that is Android 8 and above, it is mandatory for it to have a trusted execution environment hardware to obtain Google's mobile services like Google apps, etc. It's mandatory to have a trusted execution environment. Now, this isolation also prevents malicious apps from accessing this secure enclave or trusted execution environment. Mm, and the malicious apps in no form can harm this environment. Going through the companies that implement trusted execution environment, The first column basically tells about the company or the product that implements this trusted execution environment technology, and the second column tells about the hardware they use to implement this trusted execution environment. And the last column, this tells about the API standard that they use to implement this particular technology. These API standards, they facilitate the communication between our application and the trusted execution environments. Now we can see a few popular companies here, like Apple. It uses its own secure enclave on its chip, and this is a separate proprietary hardware technology, and also the API standard is also proprietary. Now we have some popular Android-based mobile phones like Samsung. It uses its own technology called TEE Gris. Now it is based on ARM Trust Zone. ARM Trust Zone is basically for ARM chipsets that the devices like mobile devices use. And now you can see the popular companies like Qualcomm, QTE. Now this also uses ARM Trust Zone as a hardware technology, and the API standard. If you see here, most of them are global platform. What this global platform means is that the global platform is an organization that it tries to make a common standard for most of the phones. It tries to make common standards or cross platform compatibility for all the phones. Or going through the next slide. Here you can see a diagram that represents this trusted execution environment. Now you can see there's something called rich OS application environment. Now this rich OS application environment, this basically is your regular processor space where you use this regular apps that do not require any additional security, and the regular computations are done here, and this is basically accessible to the user or anyone. And now you can see that there's a TE client API here that can be used to communicate with the trusted execution environment. Now this trusted execution environment, this has its own OS components, this has its own key storage space, this has its own peripherals that are used, this has its own clocks that are used, and it has all the hardware that a regular chipset has. And you can see that the trusted execution application DRM, the trusted application payment, etc., the apps that require trusted execution features that can be run here using this TE internal APIs. Now here's the description about the previous slide that we went through. Now we will be going more in detail about the hardware implementation in the next few slides. But here you can see basically it talks about the isolation mechanisms and the world of rich execution environment and world of secure execution environment. Under isolation mechanism, it speaks about the more memory partitioning that it provides, the peripheral partitioning that it provides, and the secure interrupt handling that the secure execution environment or the trusted execution environment provides. Now, Android implements something called Android Key Store. This Android Key Store is basically responsible for generating your public and private keys, your session keys, or it also is responsible for other operations like storing the keys and also generating them or importing them. Now, we'll be in this part. We'll be going through the Apple's secure enclave. Now, in this part of the video, we'll be going through the secure enclave by Apple. This is the trusted execution environment by Apple. Here, this blue part that you can see, this is basically the secure enclave of Apple, and this is a system on chip, meaning that this gray part is the normal chip, and the blue part is an isolated chip on the existing chip, and it has its own components that perform all the operations like a regular chip, just that it is a smaller chip. Now going through its features, it's a separate chip. Like I told you, it provides a secure boot process, meaning that it has a separate boot process and program. And before booting up the processor, it checks for the integrity of the bootstrap program. It has a separate encryption engine that provides performs the encryption based handling and encryption based task handling. It has a protected memory, and it also has secure storage mechanisms that store all the data securely and availability. Basically, this technology it's available on iPhone 5s onwards and iPad Air and certain MacBook models, meaning that quite uh, this is quite what we can say a common kind of technology we can say. Now, going through the hardware implementation, right now, here you can see that the secure enclave processor. Secure enclave processor, it is like a heart of the secure enclave. It is a separate chip on the Apple devices that acts as an secure island for sensitive data, you can say. It has its own operating system, stripped down version or a smaller version of the operating system designed specifically to be resistant to tampering and exploitation. Now, the secure enclave also runs efficiently at lower clock speeds, and basically, these lower clock speeds are used so that the side channel attacks are not possible on this secure enclave processor. Side channel attacks, these attacks are basically based on time or the power consumption. What a malicious actor does is he sees how much time it is being taken for the cryptographic operation, or he analyzes on the uh, power consumption by the chip, and he tries to find out some private data based on this findings. Now the next part is memory protection engine. Memory protection engine, when the device boots up, the secure enclave boot ROM creates a unique encryption key just for this memory protection task. It scrambles the data stored in the secure enclave's memory using a strong AES algorithm, which is known as ZOR mode encryption algorithm. Additionally, MAC is also calculated. This MAC basically acts as a fingerprint for the piece of data that is present in the memory, and also it uses this MAC to check the integrity of the bootstrap program. The secure enclave, it needs to access the stored data. It first checks the fingerprint. If the fingerprint matches, it decrypts the data and accesses it. If there's a mismatch, then it will flag an error basically. The latest iPhone devices, the random nonce is also generated alongside with this. This random nonce helps against any of the rainbow table kind of attacks. The entire process it has happens seamlessly on the and this secure enclave environment. Now we go to the next part, that is the secure enclave boot ROM. The secure enclave boot ROM, basically this part of the secure enclave, it helps the pre-programmed code that runs at the starting, that is also the bootstrap program, to run securely. During the startup, it allocates part of the memory to this program, and the secure enclave acts as a memory protection engine to authenticate the data stored there. Now this acts as a gatekeeper to secure enclave's operating system too. It also allows a valid signed version to run. The newer Apple devices, it plays an additional role to managing encryption keys also. Now there's also a secure enclave AES engine, you can see right here. This basically is used to generate the AES keys that are the public keys for encryption and decryption and all the other processes. This AES engine also offers a secure advantage over the software-based encryption, and this AES engine is basically a hardware-based engine, and This provides this secure enclave AES engine. This also has hardware keys derived for the sake of the secure enclave. This hardware key is basically this UID inside the secure enclave that is unique for each device, that is derived by this hardware engine during the manufacturing itself. And there's also a GID, meaning the group ID, that is derived for each of the devices, and this is unique for a particular model of the devices. And all the particular model of that, all the particular phones of that model have this unique group ID. Now there is also a public key accelerator here, PKA. This is the component inside the secure enclave that manages secure communication and data integrity. It is specifically designed to perform complex mathematical operations required for asymmetric cryptography. It offers a significant performance and security advantage too. It supports widely used asymmetric key cryptographic algorithms, and this also includes elliptic curve cryptography. Through this secure non-volatile storage is basically used to secure the data on the device, that is stored inside the secure enclave. Any of your passwords, your hash data, etc., that is stored on the device inside the secure enclave, it is stored on this non-volatile storage. This communication between the secure enclave and the non-volatile storage, it is facilitated through an I2C bus that is ensuring only the exclusive access to the secure enclave. It holds a critical element called as the entropy, which is the foundation of all user data encryption keys. This entropy is used to derive the keys basically. Now, the secure enclave has an added extra layer of security, a dedicated secure storage component. This component has several security features, including immutable ROM code, a hardware random number generator, a unique cryptographic key, and dedicated cryptography engines and physical tamper detection mechanisms are also present. Now, if we go in the latest secure enclave designs, they have something called as lock boxes. The lock boxes, they safeguard the data elements, including they safeguard this entropy and other user data using data elements, including 128-bit salt and a 128-bit passcode verifier. It also uses a 8-bit counter, an 8-bit maximum attempt value, etc. The access to the counter logbox is strictly controlled through the encrypted protocol. Now you can imagine, just by all these technologies, how secure the data has become. Even if there's a slight bit change in the data, the change is detected because there are MAC type of elements that are stored for this data, and they are stored in the form of blocks. Now the next component you can see is the secure neural engine. The secure neural engine basically this facilitates the operations like biometric verification, the biometric data storage, and all similar kind of stuff, the face ID and mm, your fingerprint scanners, etc. Moving on. Here, basically, there's a tiny summary of all these uh, things that we just spoke about. Now, I'll also attach the documentation in the last slide. This is a very tiny implementation example of how this trusted execution environment APIs can be integrated inside our projects. Now we can basically see that we can implement this by importing a global platform API, and here in this code, very basic thing that we are performing is we are checking if the underlying software is OS. Now is OS function is called, and this function basically gets the OS name and checks if the OS is iOS. This is iOS function checks if the underlying OS is iOS, and if it is iOS, then it uses the secure enclave for a secure enclave for data security. Otherwise, it uses the secure channel for Android for trusted execution for Android systems or other systems. Now, what the secure channel is basically it is the transmission medium that is used for transmitting the data between the secure enclave and the other components. Now, in this slide, I've basically included something called security for everyone. Now, in cases where somehow someone has an old device or a now, in this slide, I've included something called security for everyone. In case someone has a legacy device and or very old device that somehow managed to survive till now, now we can use other security mechanisms to basically secure data on the user's device. Now we can see that we can implement software-based trusted execution environments. There are several APIs that provide software-based trusted execution environments for devices. Now there's another technique that we can use. We can basically use Android sandboxing while developing applications on Android. We can sandbox or separate that region and make our own execution environment there. In this part of the presentation, we'll be going through the technology of SIM overlays and the FIPS 140-2 standard. SIM overlays. This is an ultra thin sticker that attaches directly to your existing SIM card. This contains a high security chip made using a semiconductor packaging processes. Now this SIM overlay, it provides additional functionalities to your regular SIM card, potentially including mobile banking, e-wallet, enhanced mobile security, etc. This is easier to be installed and it is lower cost, and it as you can see in the image here, it sits right on top of the existing SIM card, and it does not even require an extra slot. It sits directly into the slot where your SIM is residing. This is as thin as 0.2 millimeter. Companies like Chili Tag, which manufacture these overlays, they likely consider this implementation details of this particular technology as proprietary, as they do not provide any detailed information about this technology, or there aren't any documentations that show how these technologies are implemented. Moving on, CMS1 chipsets. These mobile security elements, they are a thin film patch, meaning that they are also SIM card overlays. They are like 0.2 millimeter thick. They sit right on top of your existing SIM card. They contain a high security chip protected to EAL 4 plus standard. Now, EAL is an standard. This is an international standard. EAL full forms to Evaluation Assurance Level of IT. This is for IT products and systems. It is a numeric grade provided upon completion of a common criteria and security evaluation. And this is in existence since 1999. Now, this CMS1, this technology, this performs cryptographic operations at high speeds, ensuring confidentiality, integrity, and non-repudiation. Companies with international this complies with international security standards. Now India is also trying to research in this particular field. It's trying to implement UPI payments on feature phones which use SIM overlay technology, and making UPI payments without using mobile data. Many of the Indians, especially in rural areas, they rely on the feature phones without internet access, limiting their ability to use the digital payment solutions. So, for this, companies like e-routine technologies and other companies, and even SBI is trying to research in this field to make UPI payments possible when even when the mobile data is not available, and even when specific features in the phone are not available. These SIM overlays also provide encryption and even key support to multiple types of keys. SIM overlay mobile payment film card. This enables the banking and e-wallet functionalities on most of the feature phones and smartphones. works without internet data access, relying upon encrypted SMS for communication, and employs a high security chips with EAL 6 plus certification. Now, about this, we talked in the previous slide itself. Now, EAL 6 plus certification is a quite good rating, and this also uses 3DS encryption for data protection. Now, this technology also allows you to securely send offline phone to phone and card to phone payments around the globe. Moving on to FIPS 140-2. FIPS 140-2 is a Federal Information Processing Standard publication. This is a security standard that applies to cryptographic modules. There are four levels in this particular module, each module increasing in security level, and as the security requirement increases, the level of the module also the level of the module selected also increases. The FIPS mode can be implemented in system even if the underlying cryptographic module doesn't and hasn't undergone the formal FIPS validation. Means that FIPS mode, it can be implemented. This is basically restricts the available software algorithms to the algorithms that are being verified by FIPS. This can be implemented even if the underlying hardware doesn't hasn't undergone the FIPS validation, meaning that the hardware can be vulnerable, yet the software is secure. Now, if the hardware and software both have undergone this FIPS validation, this means that the device is secure. Now, FIPS, this defines most of the things like key generation, random number generators, key establishment, key entry, etc., and cryptographic module specifications, and cryptographic module ports and interfaces, and what kind of hardware should be used, etc. Now, if you go to the previous examples, we have come across elliptic curve cryptography and other cryptographic techniques. Basically, this elliptic curve cryptography also comes under this FIPS, and it has been validated. Now, other hardware modules that we came across, like secure enclave, TEE environments, several of these are also validated by FIPS. Now, the secure enclave, particularly which is by Apple, this is also been validated. Now, several hash standards like SHA, SHA3, and triple DES, DES, AES, HMAC, all of these are also been validated. The detailed video of the FIPS standard and the SIM overlays I'll be doing in another presentation. Based on the topics that we went through previously in this presentation, I'll be going through a conceptual protocol that I designed, and this protocol does not have any of the extra features. It is only a conceptual protocol, and this can be further improved and used for multi-server authentication. And let's begin with the protocol. At the beginning, the user needs to have installed a specialized browser that supports our protocol, or the user's browser has to support our protocol. Now, we can also use an app in this place, but browser this basically helps in scaling. Once the user makes a request to the service provider, the service provider redirects him to the registration server. The registration server registers him or authenticates him and provides access to the access tokens. And using these tokens, he accesses the data that he wants to access on the service provider. Now, all the initial communication and all this authentication or the registration phase happens in a secure channel using shared secret keys or symmetric cryptography. Going through the protocol itself, in the registration phase, the user selects a user ID and a password. He computes a secret key SKU using a key derivation function, his password, and a random sort. This random sort helps him against rainbow table attacks. He then calculates the private key and also the public key using the elliptic cryptography. Then he computes a commitment for this public key. Basically, this commitment acts as an envelope for this public key, and it encrypts this public key. This can be used in the further part of the protocol. The key derivation and function and the hashing information and the parameters. These parameters and the salt are stored securely on the device by encrypting them along with the biometric data of the user. These are stored inside the trusted execution environments of the device itself. Now the user sends his ID and the commitment to the registration server. The registration server validates the user and stores his ID and commitment securely, and also the hash details and parameters necessary is stored on the registration server. In the authentication phase, the user again enters his user ID and password and computes a secret key again, using the key derivation function, password, and the stored salt. Then he computes the private key and the public key using the elliptic curve cryptography, and by using the stored iteration number. And then he computes commitment to the public key. And once he is done with that, he sends his user ID and the public key to the server. The server calculates the commitment again using that public key and verifies it against the stored commitment. And upon successful verification, the registration server provides the access tokens to the user to access the particular service provider. Now, this can also be integrated with single sign-on. This protocol can use the concept of hierarchical deterministic keys. What these hierarchical deterministic keys are is basically, uh, there is a seed generated. The seed is a random value or a cryptographic hash. We can use this cryptographic hash to derive a master key pair, meaning a public and private key pair, and this will act as a master key. This can be done using BIP32 standard for hierarchical deterministic keys. The master key should be stored securely on the user's device, and this can be used to derive further child keys through this master key. Now, this concept is very commonly used in cryptocurrency based applications. Now, these child pair keys can be used for various applications like banking and social media, etc. Even if a key that is used for a social media account is compromised, your banking key still remains safe. Now, even though this scenario is not very likely to happen, in the worst case that it happens, it still is safe. Your banking applications are still safe. Similarly, uh, you can protect other applications. Now, with this, I'll end this presentation, and I'll also include the necessary study materials. Thank you.